So there are two special limits that we want to know in dealing with trigonometric functions and their limits. These ones are going to come up for us later in our study of derivatives of calculus. But for right now, we're going to take these on faith. The first one goes like this. It says that if we take the limit as x approaches 0 of the sine of x over x, we're going to wind up with 1 as its value. Kind of interesting. We don't want to take anybody at their word, but for right now, let's just take it on faith. That's what that limit is. Then we wanted to look at the limit as x approaches 0 of 1 minus cosine of x over x, and we find that that value is equal to 0. So how do we use these limits? Let's go through a couple of examples of using them first, and then I'm going to go in another video and we'll prove this first one here, which should be an interesting exercise. Okay, now the thing about this limit right here, the limit as x approaches 0 of sine of 3x over 4x, we have to be very, very careful in what we mean right here. The argument, that is the variable that we have in the numerator and the denominator, have to match exactly for this to be true. Notice that this says the limit is sine of x over x, right? But this is the limit as x approaches 0 sine of 3x over 4x. They don't match. So what could we do? Well, one way of handling this is to rewrite our expression. Let me show you how we can do this. And I'm just going to do it in 2 steps. If you recognize it, you can actually do this in just 1 step. But let me run it through it. 3x, we actually have to have 3x down here in the denominator. We've got 4x, but it's not as though we can subtract something. So here's what we're going to do instead. We're going to rewrite it recognizing that we're going to be taking the limit as x approaches 0 of 1/4 of the sine of 3x divided by x. So what we would do right here, just take that constant outside, right? We're 1/4 times this limit. Now, the other thing that I would point out right here is that we want 3x in the denominator. So what we're going to do instead is we're going to multiply in an extra 3 here, right? So this is actually going to become, this is like a multiplying by 1, right? We can always multiply by 1. We don't change the value of the fraction. So it's like we're taking the limit as x approaches 0 of 3 times the sine of 3x divided by x times 3, which is to say 3x. Well, this 3 is a constant, and it can also come out, so it's like we're taking 3/4 times the limit as x approaches 0 of the sine of 3x divided by 3x. Now, this is the kind of limit that will equal 1, right? The argument here must match the argument here. So now they do, right? We've got 3x in the denominator. We've got 3x inside of our sine function. So when we take its limit as x approaches 0, we're left with 3/4 times 1, which is to say that our full limit right here will be 3/4. All right. Now, a very similar thing holds when we talk about this limit. The limit as x approaches 0 of 1 minus cosine of x over x. We'll note that this limit must come out to equal 0. All right, so what do we do? Well, here's a interesting function. Let's say we've got the limit as theta approaches 0 of secant of theta minus 1 over 2 theta secant theta. Now, one thing that we'll note right here is that this is the kind of function that if we use direct substitution, we're going to get the secant of 0 minus 1 divided by 2 times 0 times the secant of 0. And, well, this is like saying 1 minus 1 divided by, well, 2 times 0 times anything is just going to be 0. So we end up with 0 over 0, and that's indeterminate. When we get an indeterminate value, what we try to do then is rewrite the function in such a way that we can take advantage of any special limits or something like that. Well, here's a special limit that looks like this might be related to, so let's rewrite. Our Secant function is the reciprocal of cosine. So we're going to be taking the limit as theta approaches 0 of 1 over the cosine of theta minus 1 divided by 2 theta times 1 over cosine of theta. So what we should do then is to multiply the numerator and denominator by cosine of theta to get an equivalent expression. So I'm going to multiply my numerator by cosine of theta and the same thing in my denominator. Right? Multiplying by cosine of theta over cosine of theta is equivalent to multiplying by 1. Multiplication by 1 doesn't change the value of the fraction, so we're going to be taking the limit as theta approaches 0 here of cosine of theta times 1 over cosine of theta, that's 1, minus 1 times cosine of theta, which of course is minus cosine of theta, divided by 2 theta. Now again, right, our arguments should match right here, just like we talked about on the left. If we have 1 minus cosine x over x, well, that's fine, it will be equal to 0, but over 2, well, we can factor that out, right? This is really like saying 1/2 times the limit as theta approaches 0 of 1 minus cosine of theta over theta. And now this is more recognizable because we know that as theta approaches 0, this quantity will end up equaling 0. So we end up with 1/2 times 0, and so our overall limit must also be 0.